Question number 9 asks, what happens to the pH of an acid when 10 cc's of it is added to 90 cc's of water? So they've increased it by 10% because it's 100 milliliters of water. So the concentration of H plus is going to decrease when you add the water. So your pH is going to increase. And if you wanted to go on and realize it's probably going to increase by 1 unit, that's fine. Since it was increased, tenfold with it, then that's fine. But all you really need is that the pH, that concentration decrease so the pH increases. Number 10, beer has a hydrogen ion concentration of 1.9 times 10 to the minus fifth. What's its pH? So you simply take the negative log of the 1.9 times 10 to the minus fifth, and if you put that into your calculator correctly, I came up with a pH of 4.72. And number 11, an aqueous solution has a pH of 9 at 25 degrees. What are its concentrations for H plus and OH minus? So since the pH is 9, I can assume that the concentration for H plus is the negative log of that, or I can take the exponent of that, so it should be 10 to the minus ninth. And since the product of H plus and OH minus has to be 10 to the minus 14th at 25 degrees, then I can assume the OH minus is the other 10 to the minus fifth. And again, that's knowing that the Kw constant is 10 to the minus 14th at 25 degrees. Number 12 says, for each of the following solutions, calculate OH minus from H plus or H plus from OH minus. Classify each as acidic, basic, or neutral. So if the H plus is 3.4, this is all operating around the concept that I have Kw equal to 10 to the minus 14th, which is also equal to my H plus times my OH minus. So if I know my H plus, I can sub it in here, or basically I can take 10 to the minus 14th divided by whichever concentration I have. So if I take 10 to the minus 14th and I divide by 3.4 times 10 to the minus 9th, I come up with an OH concentration of 2.94 times 10 to the minus 6th. Is it acidic or basic? Well, anytime the H plus is more than 10 to the minus 7th, it's going to be basic. Or if I compare these two, this is a smaller number. There's less H plus, there's more OH plus. So it's basic. B, if I take 10 to the minus 14th and I divide by the 0.010, I come up with an H plus concentration equal to 1.0 times 10 to the minus 12, or just 10 to the minus 12. And again, my H plus is very small, my OH minus is much greater, so this is a basic solution. C, 1 times 10 to the minus 10th is the OH, so this one's pretty easy. It should be 1 times 10 to the minus 4th for my H plus. This time my H plus is greater, so it's acidic. And D, 8.6 times 10 to the minus 5th. This one I have to actually divide the 10 to the minus 14th by this value, and I get an OH equal to 1.2 times 10 to the minus 10th, which again, the OH is less than the H plus, so this is also acidic. Number 13, what is the pH of 0.01 moles per liter solution of HCl which dissociate fully? So this is my concentration of H plus, and all the H is going to come off and just one H per molecule comes off. So for number 13, if I take the negative log of 0.01, I get a pH equal to 2.0. For number 14, for each of the following biological fluids, calculate the pH from the given H plus or OH minus. Now they want pH regardless of whether they give you H plus or OH minus. So for A, if I have OH minus, I can go ahead and either take the negative log of that and then subtract from 14, or I could take this and divide 10 to the minus 14th. So I've got two ways to do A. I'll show you both ways, and then I'll just give you one solution after that. So I can take 10 to the minus 14th and divide by the 8 times 10 to the minus 8th. And if I do that, I'm going to come up with, let me just grab my calculator here. I get 1.25 times 10 to the minus 7th. That's my OH concentration. And so now if I take the negative log of that, I get 6.9 as my pH. And take back, this is my H plus because I started with OH. So by dividing that, I get the H plus concentration, and when I take the negative log of this, of 1.25 times 10 to the minus 7th, I then came up with 6.9. The other way to do it would be if I took the negative log of 8 times 10 to the minus 8th, so I'll put parentheses around that, and if I take the negative log of 8 times 10 to the minus 8th, I get 7.1, and then that's my POH. So if I subtract 14 minus 7.1, that gives me 6.9 for my pH. Either method works, and so I can do the same thing for B and C, and I'm a slide up here, so I've got a little room to work. So looking at B, I think it's easier to go ahead and take the get the pH or POH. In this case, it's already H plus, so the pH of that is just going to be 2. That one's pretty easy to see. And then C, not quite as easy to see. It's the OH, but I'm going to go ahead and take the negative log of 6 times 10 to the minus 10th, and that's going to give me negative log. This gives me 9.2, so again, 14 minus the 9.2 is where I get the 4.8 from. And I'm going to clear a little space here so I can squeeze number 15 on yet. So number 15 is a little bit of work. It says 6 grams of NaOH is added to 1 liter of water. What's the pH of the solution? Assume that NaOH dissociates completely. So first thing I need to know is how many moles I have. 6 grams of NaOH is approximately 40 grams per mole. So I go ahead and take my 6 and divide by 40. And I've got 0.15 moles in a liter. So now I can take the negative log of 0.15. And I come up with a pH, well, actually an NOH of, take the negative log of, struggling here, of 0.15, and I get 0.82, but that's my POH. So when I take 14 minus that, I come up with 13.2 approximately for my pH. Number 11, two acids X and Y, both of concentration 0.2 molar, have pH values of 2 and 4. So the same concentration. So the difference in 2 and 4 is whether it's polyprotic or monoprotic, or if it releases all of its H plus or not. So the 2 releases is got more H plus in there than the 4 does. So X is a stronger acid than Y. That's true. Y is more dilute than X. Not necessarily. That refers to concentration. And it already says that it's the same concentration. So no, it's not more dilute. They're the same concentration. X contains more undissociated molecules. No, X apparently dissociated all of it or nearly all of it. And Y contains a higher concentration of H plus. No, these two statements are just the reverse. Y contains more undissociated, and X contains a higher concentration of H+. So only A is true.